Good afternoon, everybody, or good morning if you're somewhere out west, or I guess good evening if you're in Croatia or something. But we welcome you to our review of the April 13th, 2020 tornado outbreak in the Midlands of South Carolina and the CSRA of Georgia. This outbreak also included many other parts of the state of South Carolina, but we were concentrating mainly on the area that we're responsible for. We had a number of staff involved in this process, and 4 of those folks are going to give different presentations for you today. So as an outline, we're going to start with a synoptic overview of the situation with forecaster Chris Rohrbach, then a mesoscale investigation with presenting by forecaster Tony Petrolito. Then we're going to have a look at the remote sensing of the event, looking at satellite imagery, GLM, and radar, and that's going to be presented by Dan Miller, forecaster, and then the survey process, and that's going to be done by meteorologist Leonard Vaughn, who also happens to be our service hydrologist. So a couple of ground rules, a couple things for you all to know. This session will be recorded and will be put on our YouTube channel afterwards, so you can review it again at a later time if there's some part of it that you missed. Everyone will be muted during the presentations. Each presentation will be anywhere between 12 and 15 minutes, but there will be plenty of opportunities for question and answer. To keep the flow of the presentations going, we will allow for maybe one question after each presentation, but most of the Q&A will take place after all the speakers have completed and will all be available for whatever Q&A is going on at that time. So if you have questions that you think of during the presentations, please type your questions either into the question box or into the chat. And then once we get to the Q&A session at the end, we'll also have the availability to unmute you if you have a specific question, if you raise your hand to ask a question. So those are all the ground rules. I know everybody's time is limited, so I want to get going here, and I'm going to pass it over to our first speaker, Chris.
All right, good afternoon, everyone. Today, in our first out of our 4 presentations, we'll take a look at a brief climatology of tornadoes in South Carolina, and also a synoptic overview of the April 13th event. And then finally, we'll take a look at the Gfs forecast performance. First, we'll look at a local climatology that was actually put together by one of our summer students, Alexander McGinnis. Not so surprising result from the climatology is that April is a favorable month for tornadoes in the state. April actually had the highest tornado count out of any month on average. But what is very interesting is the diurnal timing of last year's event. If we look at the climatology broken down by hour here, tornadoes in South Carolina are typically favored during the peak heating hours in the afternoon, especially significant tornadoes. But during the April 13th event, all South Carolina tornadoes occur between 3 a.m. and 9 a.m. We took a closer look at that time frame here. It's the same graph, just cut off. We can see that from 1950 to 2019, South Carolina has only had 8 significant tornadoes during that time frame. However, during last year's event, there were 12 significant tornadoes alone during those hours. It was already a historic event for South Carolina, but what makes it even more fascinating is that we had so many significant tornadoes at such a diurnally unfavorable time. We'll take a quick look here at the synoptic scale setup. The smaller scale features and radar signatures will be covered in later talks today. Here we're looking at the 250 millibar heights and wind speeds. We can see a strong upper level jet moved into the southeast on the night of the 12th. This would lead to strong upper level divergence over the region and provide support for convection on the morning of the 13th. In conjunction with that upper jet was a pronounced 500 millibar shortwave. The shortwave will lift out of the deep south and over South Carolina on the morning of the 13th. In addition, there was an extremely strong low-level jet, which would end up being crucial for creating an environment favorable for tornadogenesis. Warm, moist advection ahead of a cold front was responsible for creating a conditionally unstable air mass. Because of the nocturnal timing of the event, the jet would be the main player in warming the low levels. To assess the performance of the GFS, I compared it to the Global Data Assimilation System, GDAS. For this presentation, I used the 6Z GDAS at forecast hour 3, and that was chosen because it was the closest time to the first tornado for the area. So all the following images you'll see will be valid at 9Z on the 13th. Both the GFS and the GDAS datasets were pulled from the NCAR Computational and Information Systems Laboratory with a 0.25 degree spatial resolution. 41 GFS forecasts were analyzed. Those forecasts were subjectively separated into 4 time periods based on the synoptic pattern and the potential for convection at 9Z. During the extended period, which you can see defined on the screen here, there was low scale among all of the forecasts. Each of the runs indicated a stable air mass over the region at 9Z. In the long term, there was increasing consistency between the runs, but overall the GFS was still too progressive with the upper level trough that we'll look at here shortly. The mid-range period was characterized by a significant increase in skill in the GFS. During this period, the model became gradually less progressive with the upper trough. We'll take a closer look at that a little bit later. And then finally, in the near term, although the synoptic and mesoscale patterns remained fairly skillful in the near term, surface-based CAPE values were under forecast by almost every run. The image you see here shows the average 250 millibar heights from the GFS during the extended period. The blue contours show the average 250 height from the GFS, while the black contours are the GDAS verification at 9Z. The shaded areas are the average bias in the GFS forecast during this time frame. As you can see, on average, the GFS was much less amplified with the synoptic pattern. This may have partly been due to the timing differences between each run, although for the most part, the individual runs generally had zonal flow over the eastern US at 9Z. The average bias decreased in the long term. On average, the GFS showed troughing over the central US, but was still too progressive with the overall pattern. The axis of the ridge off of the East Coast was well east of what ended up verifying. And again, we'll take a closer look at the mid-range period later, but this is when we generally saw increasing performance from the GFS and the synoptic pattern. The ridge axis was much closer to verification, as was the amplitude of the trough. And as you might expect, the near-term period was closest to verification. However, the smaller scale factors were the main influence on forecast skill for the near term. Since the timing of this event is so unique, I'd like to quickly look at a study by Kiss and Straka, which was published in Weather and Forecasting in 2010. The authors reviewed nocturnal, non-tropical tornadoes across the US from 2004 to 2006. Their goal was to find environmental discriminators between significant and weak tornadoes. They found that QLCSs were accounted for the majority of nocturnal tornadoes during those years. The majority of the significant tornadoes they evaluated were generally accompanied by an exceptionally strong low-level jet. For the sake of time, I won't get too much into the charts you see on the right, but I'll mention some of the values in the coming slides. If we take a closer look at the 500 millibar heights during the long term, or during the midterm, excuse me, we can start to put together why the scale improved. Here on this image, the lighter blues correspond to older forecasts, while the darker blues are newer forecasts. We can see that the ridge axis shifts further west during this time, as does the shortwave. It's a little slower to arrive in South Carolina. This led to stronger difluence over South Carolina and aided the development of a low-level jet with a strong southerly component, which, as you remember, was one of the key factors in the Straka study. Looking at the left-hand image, we can see individual GFS forecasts of surface to 850 millibar bulk shear during the midterm period. You can see that the low-level jet is slower at the beginning of the midterm, but becomes slower and has a stronger southerly component in later runs. On the right-hand side, we can see verification from the GDOS, which show low-level shear with values around 50 to 60 knots, very strong. We can't compare these values directly with the study because the study was using 0 to 1 kilometer shear, and these values weren't available for the GFS data set that I examined. But in either case, this would have constituted an exceptionally strong low-level jet. In response to the westward shift of the jet, we see a large increase in 0 to 3 kilometer storm relative helicity values. The GFS verification indicated SRH values exceeding 500 meters squared per second squared over most of the region of interest. The median 0 to 3 kilometer SRH values for significant tornadoes in the Straka study was 477 meters squared per second squared. Warm moist advection increased over inland areas during the period, that is the midterm. We see this reflected in the forecast surface-based Cape values from the GFS. Weak potential instability at the beginning of the period rose to over 700 joules per kilogram by forecast hour 51, though this was still significantly lower than what we see in the GDOS verification on the right. In the near term, the synoptic scale setup remained fairly consistent. The GFS was able to maintain the strong low-level jet over the region, as well as many of the parameters identified by Straka at significant thresholds for significant tornadoes. Although we'll see, even in the near term, the GFS significantly underestimated the instability for the event. Now, according to Straka, Cape was not a good discriminator between weak and strong tornadoes or their nocturnal cases. But in general, instability is still an important factor to tornado genesis. So we'll take a look here at what the GFS said forecast. The graph here you see of surface-based Cape values is divided into the 4 time periods that we examined. Oldest forecasts are on the left, with newest on the right. These point forecasts were taken at the grid corresponding to the Orangeburg ASOS, which was a fairly central location to the tornadic activity during the event. We can see surface-based instability wasn't consistently present in the GFS until the midterm, and then we started to see the slower progression of the low-level jet. But even during the near term, we can see that surface-based Cape values were drastically under forecast compared to the verification, except for right up to the event. You can see a very similar trend here in the surface-based lifted index values. LI values became consistently negative during the midterm, but we're still under forecast for almost all periods. In summary, the synoptic scale pattern was very favorable for significant tornadoes to occur on the morning of April 13th. An exceptionally strong low-level jet may have played an important role in the 12 significant tornadoes that developed. The GFS began to indicate an increasing threat for severe weather and tornadoes in the midterm. However, nearly all of the models, or all of the model runs, failed to show the higher instability values that we saw during the event. According to the Kiss and Straka study, SRH and bulk shear were good discriminators for strong nocturnal tornadoes. And in those regards, the GFS performs very well in the mid and near terms. For further research, we like to look at other global models as well as their ensembles to see how the GFS compared to those. It would also be useful to determine if the GFS indicated potential for severe weather at times near 9Z. In other words, was the poor skill in the long term and the extended due to a timing issue? Could the GFS have been indicating that there was potential for significant weather at some point other than 9Z? And we'll take questions and comments at the end, or if you want to type them into the chat. Thank you.
Thank you, Chris. We have no active questions now, so what I'm going to do is pass it to our next speaker, Tony Petrolito.
Okay, this will be a mesoanalysis review of the tornado outbreak across Central South Carolina and East Central Georgia. We're going to do an overview of the environment. I'll briefly touch on some of the model forecasts, but concentrate on the observed data. We'll be looking at the shear and instability with a focus on the CAPE, the storm relative helicity, and the EHI. I'll also look at other composite parameters. We'll also go over the climatological perspective and finally a summary. I want to start off with a 4-panel of the observed data around 6Z, a few hours before the tornado genesis. We'll look from the surface to 500 millibars to give you an idea of the low to mid-level shear and moisture transport and temperature into the area. And looking at the winds, the kinematic profile during this time period, it was actually very strong. Just off the deck, the winds were increasing to near 50 to 60 knots, 70 knots up to above 850 millibars. And this was all ahead of a relatively strong shortwave trough that was negatively tilted coming out of the lower Mississippi River Valley. At 500 millibars, you can see that 100-knot jet streak just to the west of the area. The kinematic fields showed strong varying with height. So we had very strong wind speeds and directional shear. If you look at 925 millibars, you can see that the moisture was increasing across central and eastern South Carolina up the Savannah River as the southerly low-level jet was increasing. As we move on to 9 Zulu, you can see this is near the time of the tornado genesis. The 850 jet, like Chris was talking about, increased to almost 80 knots, around 80 knots in the Central Savannah River area. And this was increasing the moisture across central and eastern South Carolina. It became quite deep into the mid-levels. And if you look at 500 millibars, you can see that jet streak setting up just to the west. And the region along the Savannah River was in that right entrance region of the jet. And at this time, I don't show it, but the divergence was increasing significantly across the area. And the upper lift was quite impressive. Okay, here is an observed sounding from Charleston at 12Z that morning, but it's representative of the environment across Central South Carolina and East Central Georgia during the overnight period. And you can see from the sounding that you can see that deep moisture up to the mid-levels and relatively strong CAPE. Very unusual to have this kind of instability late at night, like Chris was saying, into the early morning hours. And of course, compared to the GFS, this instability was a lot stronger. The surface-based cape was around 1700 in this sounding. Notice the LCL was relatively low at 693 meters. That can be favorable for tornado genesis. The precipitable water was near record. It was actually a record for the date in Central South Carolina, but this sounding shows 1.8 inches. And the bulk shear, talking about the bulk shear, you can see 75 knots of bulk shear. Values over 30 to 40 favor supercells. The 0 to 3 kilometer storm relative helicity was at or above 500 meters squared per second squared. Values over 100 increase the threat for tornadoes. And again, getting back to the instability, there's a study back in 2009, Jackson and Brown. They found that a cape greater than 1,500 joules per kilogram was associated with significant tornadoes across the southeast, mainly in the deep south. And I'll talk a little bit more about this study later in the presentation. Looking at the bad wind profile that was we generated from, the bad wind profile data hodograph valid at 09 Zulu near the time of tornado genesis. You can see that the hodograph, has that appearance of the sickle, and it's more indicative of a Midwest, supercell. Very strong wind fields here. 0 to 1 kilometer shear was approaching 60 knots. So most of the deep layer shear was in that lowest 0 to 1 kilometer. Up to 0 to 3, it increased to about 73. So it is, most of the shear is in that lowest 1 kilometer. Okay, I'm going to compare some Buffkit model data. This is near the time of tornado genesis, comparing the short range ensemble with the RAP model at Orangeburg, and this was valid at 10Z. And you can see that pretty good agreement in the models at this time, these shorter range models compared to the GFS. They were higher with that cape, above 1,000. The cape was a little bit stronger than what the models were indicating. The EHI was 2 to 4. That turned out to be underestimated. The helicity is also underestimated, 350 to 470 maybe in the model guidance. But in general, there was good agreement as we got closer to the event. After 6C, the short range models were in pretty good agreement. You can also notice that the LCL on both these models was relatively low, 290, 500 meters. So they were in agreement on that predictor. Okay, looking at the instability parameters, I want to compare cape and lapse rates. The most unstable cape around 6C was 1,000 to 2,000 across the area. And if you look upstream, the lapse rates were steeper across central Georgia, and that more instability was going to spread into the area towards tornado genesis around 9Z or so, as the shortwave trough lifted to the northeast. Colder temperatures allowed. Looking at 6C LCL was around 500 meters, like I was saying. So that's favorable for tornado genesis. And also that moisture was deepening significantly across the area as the southerly flow increased. You can see that the precipitable water was well above normal for this time of year, 1.5, 1.6. There was a dry slot over central Georgia, but moisture was increasing across western Georgia ahead of the cold frontal boundary. Now, low LCL and higher boundary layer moisture will tend to discourage any rapid low-level cooling through evaporation in the subcloud layer. And this results in a weaker outflow. So less interference with any developing near-surface circulations that could become tornadoes. Okay, at 9Z, you can see that those steeper lapse rates are moving into the lower Savannah River area or Central Savannah River area. So, that was the area of concern. Things were starting to point to the Central Savannah River area for tornado genesis. And you can see that the instability increased to around 2000. So at this time, near tornado genesis, we had strong and deep instability that can support long-lived updrafts. Okay, comparing the 0 to 3 kilometer mixed layer cape and surface vorticity. Okay, the 0 to 3 kilometer mixed layer cape was in the 100 to 125 joules per kilogram range. And strengthening surface vorticity can be seen near the time of tornado genesis. We have vorticity advection spreading north from the low country of South Carolina near Savannah. Okay, so that's advecting north. And then we have another vorticity trough just west of the Augusta area that's moving east. Now looking at surface moisture and temperature along with vorticity at near the time of tornado genesis. The vorticity is the shaded color this time. You can see that there's increasing moisture convergence across the area, especially over east central Georgia and along the coastal plain of South Carolina. And there's that pronounced Theta E ridge in eastern South Carolina as the instability is increasing across the area, contributing to the instability. And there's that moisture convergence as we move to 10Z. It does appear to increase across central South Carolina and the CS array a bit ahead of that vorticity. And I've seen moisture flux convergence increase near other tornado cases in the past across central South Carolina. So, this moisture convergence may be a predictor to look at because it can probably enhance the updrafts and maybe maybe result in the vorticity being tilted into the updraft more efficiently, the horizontal vorticity. Okay, looking at the storm relativisticity, like we were saying, it was quite strong. The 0 to 1 kilometer storm relativisticity was ranging from anywhere between 500 and over 600 meters squared per second squared. And if you look at the 0 to 3 kilometer change in storm relativisticity, it was increasing across central and eastern South Carolina at 6Z. As we move to 9Z, the storm relativisticity increases a bit. And if you look at the change in storm relativisticity, there's this couplet that is apparent in the data. Okay, so it's increasing across eastern South Carolina, and then you have this sharp gradient as the storm relativisticity is weakening to the west. This may be, important in the tornado genesis. This gradient that you see here, this couplet. Found that a little bit interesting.
About 2 minutes, Tony.
Okay, I'll try to move ahead. I want to get back to the Jackson and Brown study. They looked at severe weather cases across the Deep South, primarily from the lower Mississippi Valley east across Georgia. Didn't include South Carolina, but I think this is representative data. They determined the mean values for different storm types of thermodynamic and kinematic variables. And so between non-tornadic supercells, non-significant tornadoes, and significant tornadoes. And what they found looking at the mixed layer cape was it was nearly constant across all storm types due to the deep moisture and associated weak low-level lapse rates typical across the Deep South. In South Carolina, the moisture decreases during the fall and winter a bit. So, but anyway, our mixed layer cape for this case was 125, which is well above the 75th percentile of all the distributions. So that may be, above 100, you might want to be concerned if you see that in the mixed layer cape. The 0 to 1 kilometer mean storm relativisticity was much higher for the tornadic environments when compared to non-tornadic. You can see the medians are separated, so this is better. There is a strong statistical significance here. But in our case, it maxed out, the 0 to 1 kilometer storm relativity maxed out around 600, which is well beyond these distributions. Okay, looking at the AHI, the 0 to 1 kilometer and 0 to 3 kilometer, considerably higher for tornadic versus non-tornadic from their study, statistically significant. And in our case, again, well beyond these distributions. We had 6 to 7 in the 0 to 1 kilometer, and for 0 to 3, that EHI was greater than 8, actually closer to 10. Looking at the EHI again from 9Z, you can see that maxima down in the Central Savannah River Area, 7 to 10, and that's where the tornado genesis developed. Other composite parameters were also quite useful, especially the significant tornado parameter. You can see all these values are extremely high for our area. And as we move to near tornado genesis, again, you see that bullseye right over the Central Savannah River Area into the southeastern Midlands. Okay, and again, looking at significant tornado parameter at 10Z, very high, 11, which is unheard of in this part of the country. Precipitable water, we were actually a record for the day, well beyond the 90th percentile, 1.9, which is extremely high for this time of year. Looking at the climatology, you can see that this case is the red arrow, so you can see all the values are well above the climatology on all these elements, except for the mixed layer Cape. We're a little bit lower, but again, that may not be as important as we thought. You know, so but it was higher than the 70th percentile in the study that was done. And the LCL is lower, so that's actually more favorable. So in summary, this was a highly anomalous environment for this part of the country, even for the Central Plains. Significant strengthening of the shear and instability was seen in that 3 to 6 hour period preceding the tornadoes. The precipitable water was around 1.9 inches, which was a record for this date. And the composite parameters were extremely high and well outside of the climatological database. And the EHI is a very useful predictor of tornadic storms in the southeast from the study done in 2009. And it was anomalously high for this event. And I really think using the EHI is a good predictor for tornadoes in the southeast.
Thank you, Tony.
This is for further information.
We're going to need to move on to Dan for the next presentation.
Okay, Frank, thank you. We're going to start with a regional infrared satellite loop. This is a 21-hour loop starting the previous day. The severe weather with this system started on the morning of Sunday, April the 12th in the lower Mississippi Valley, and it was in the form of convective clusters. And the convection appeared to organize into a quasi-linear convective system across Mississippi and Alabama on Sunday evening. And then that moved east into our forecast area early morning, Monday, April the 13th. In this particular enhancement, the red color is showing you your cooler cloud tops and your higher cloud tops, and there tends to be a rough correlation between the higher storm tops and the strongest convection. And let's take a closer look. This is a 3-hour infrared satellite loop at 1 minute intervals going from 4 a.m. to 7 a.m. Eastern Daylight Time. And in this enhancement, the cooler cloud tops, higher cloud tops are in the dark red. So watch this area right in here, the Central Savannah River Area and Southern Midlands right there. You see those cloud tops growing and developing. As it moved into that axis of the combination of strongest instability and shear that Tony mentioned in the previous segment. Infrared imagery is a good tool for identifying those cooler temps associated with the higher cloud tops. And as a reminder, since this was late night, early morning, we did not have visible satellite imagery available to us due to darkness. One of the pieces of information that the geostationary satellites can provide us also with is lightning information. There's an instrument on board the geostationary satellite called the Geostationary Lightning Mapper, or GLM, and it detects lightning by measuring the light that's given off by the lightning. And it works best at night when you don't have interference from sunlight reflecting off of the cloud cover. And it does not differentiate between cloud to ground or intra-cloud lightning. But the important thing about GLM is looking at the trend in lightning activity. This is a 12-minute animated GIF. We get GLM data every 1 minute. So in that 12-minute period of time, as the stronger part of the convective line was approaching our county warning area, a segment of the line started showing a significant increase in lightning as it was moving towards the northwestern part of Burke County, Georgia. And a lightning jump signals a strengthening updraft and therefore an intensifying storm. And so, and it could possibly signal a storm that could become severe. A lightning jump does not necessarily mean that that storm will become severe, but it does indicate that that storm is strengthening. And in a very unstable, highly sheared environment, that is a storm that you need to watch out for. And this lightning jump could be a precursor to a severe storm or tornado touchdown. And in fact, in this case, it was. We saw the lightning jump in the 12 minutes up until this time here, 08:53Z, which is 4:53 a.m. Eastern Daylight Time. That was the time that we had our first tornado touchdown in Burke County, Georgia. This is a map of the tornado tracks in our county warning area, the area bounded by the red line. We serve much of Central South Carolina and 5 counties in East Central Georgia. We had 8 tornadoes that morning, and 5 of those reached EF3 status on the enhanced Fujita scale. As I'm sure you know, the enhanced Fujita scale is a scale that measures tornado intensity on a scale from 0 to 5, with 0 being the weakest, 5 being the strongest. We've never had an EF5 in South Carolina. The storms were moving pretty quick. They were moving at about 50 knots or about 60 miles an hour. So this area moved through our county warning area fairly quickly. The total length of time between the first tornado touchdown and the last tornado dissipating was about 1 hour and 44 minutes. And there was a time here for about 1 minute, right around 05:50 to 05:51 a.m., where we actually had 4 tornadoes in progress at the same time. And I'll show a radar image of that here in a minute. Let's take a look at a regional radar loop as showing the convective line as it's moving across Georgia and through our county warning area. The time at the top of the image is in standard time, so add an hour to get daylight time. One thing that's interesting is the line moves through the Central Savannah River Area in southern Midlands. You see a very pronounced comma head develop on the line, and indicative of rotation developing in that segment of the line. So let's take a look at it again. The convective line is moving towards this CSRA. Take a look at this area right here. You got a nice comma head that develops right there and moves across into the Savannah River site in southern Midlands. Let's take a closer look at some of the notable radar signatures. I mentioned earlier, tornado number 1 was the one that touched down in Georgia. This is tornado number 2 that touched down in the Savannah River site. And this is at 09:30 Zulu or 05:30 a.m. Eastern Daylight Time. This tornado touched down 9 minutes before this screen capture. At this time, at 09:30 Z, this tornado was at EF3 intensity. Looking at the upper left panel, this is your base reflectivity. You have a nice hook echo. an enhanced reflectivity signature at the tip of the hook. In the upper right, we have storm relative velocity. That's Doppler radar has the ability to detect motion in the atmosphere. The Columbia radar is to the northeast of this circulation. These blue colors here showing motion towards the radar, the orange and reds showing motion away from the radar. You have strong, what we call gate-to-gate rotation right in there. The difference between the inbound and the outbound gives a rotational velocity of 50 knots, and that's well above our normal concern threshold of 25 knots. In the bottom right, this is GR2 analyst software that we're looking at. A product that's available in GR2 is a product that measures the strength of the rotation or the degree of azimuthal shear that's taking place over a certain distance, and a product called the normalized rotation, or NROT. And a local study that was done here in Columbia indicated that NROT values of 1.0 or higher are a concern threshold and typically associated with most tornadoes. And in this case, you can see the NROT was well above that at 2.11. And it's unusual to have NROT values above 2 in our county warning area. And one of the another significant and interesting image here, the lower left panel, this is the correlation coefficient. The correlation coefficient is a product that gives us information about the size and shape of the objects that the radar beam is bouncing off of. It's a dual polarization product that sends out radar pulses in both the horizontal and vertical planes and measures the difference in returned energy from both of those planes from pulse to pulse. Now, in most cases, in most rain situations, most of the raindrops are generally the same size and shape. So you get high correlation coefficient values that's painted in the red and purple and magenta colored areas. But when you start introducing mixed precipitation types, or especially for non-meteorological targets, such as debris from a tornado, where you have objects that vary greatly in size and shape, you get very low values of correlation coefficient. And in this color scheme, it shows up very nicely here in the blue colors. That is radar confirmation of debris being kicked up by the tornado. And when I say debris, that doesn't necessarily mean structural debris. That could be vegetative debris. And in this case, it probably was. The Savannah River site is a heavily forested area, mostly pine trees. So what you're seeing is debris from damaged trees, tree limbs, pine needles, bark, even dirt. It can get kicked up by the tornado and give you that very good debris signature in the CC product. This is a cross section using GR2 of the correlation coefficient product at 0939Z. This is for tornado number 3, which also touched down in the Savannah River site, just northwest of Parr Pond. The tornado touched down 6 minutes before this cross section was taken. The tornado achieved EF3 status in the Savannah River site, and then it weakened to EF2 as it emerged out of the Savannah River site boundary when this capture was taken. And the interesting thing about this image is the lower values of correlation coefficient in the green and blue. You can see the debris that was kicked up by the tornado was lofted well up into the atmosphere, up to 15,000 feet, and then carried aloft by the strong winds aloft. So very interesting image there. As I mentioned earlier, we had 4 tornadoes in progress at the same time. This is what the radar looked like at that time. This was 0951Z. That's about, let's see, that's 12 minutes past the time of the cross section that I just showed. That tornado number 3 dissipated at 0942Z, but at 0951, tornado 2 was still in progress. Tornado 4 had just formed. Tornado 5 only lasted 2 minutes, and then tornado 6. You can see the nice rotations in the storm relative velocity on the left and the NROT values on the right. Tornado 4, it was the strongest circulation at this time, and it would go on, unfortunately, to cause 2 fatalities and 7 injuries about 10 minutes after this. in Orangeburg County. Tornado number 4 tornadoes 2 and 4 ended up crossing paths, which is kind of unusual. Tornado 4 ended up moving kind of up and ahead of tornado 2, and then tornado 2 kind of dissipated behind tornado number 4. This is at 0952Z. You can see a nice hook echo from tornado 4. You can see the rotational couplets from both tornadoes and the debris signatures from both tornadoes. This is as it's crossing over from Barnwell County into Orangeburg County. At 0958Z, tornado 4 had kind of slipped ahead of tornado 2. You can see hook echo and enhanced debris signatures from both tornadoes. And looking at the right image here, the correlation coefficient, you can still see debris from both the tornadoes in progress. Up here at the top, that is residual debris that was kicked up earlier by both tornadoes 2 and 3, lofted up well into the atmosphere and then carried along by the strong winds aloft. And at 0602Z, unfortunately, we had the 2 fatalities and 7 injuries at this location where I have the white dot just northwest of the town of Nices. The tornado 2 had dissipated and its debris was wrapping around cyclonically or counterclockwise around the stronger circulation of tornado number 4. So that was a sample of some of the more notable radar and satellite images from this event. And now I'll pass it back to Frank to introduce the next phase of the severe weather event, which is the storm survey process. Thank you very much.
Thank you very much, Dan. Yep, I appreciate it. It was excellent. And now I'm going to pass it to Leonard Vaughn, who's going to talk about the storm survey process.
Okay. Yeah, I'll get on here with talking about the storm survey process, and obviously some of the challenges that came with this event, and we'll cover those as we go through the presentation. Yeah, you know, things that are really important when we have events like this is, you know, we really need to know like what happened. Obviously, based on some of the information you've already seen, we had a pretty good indication of the potential of what happened with the event. But knowing what happened, what type of damage, where the damage was located, those are extremely important. And also, when did it happen? And we can base a lot of that on the radar, but it helps to have information from not only our partners in the emergency management community, but also public and any kind of reports we can get even from like spotters and those types of people. And the reason why this is so important is the whole survey process is one large process, and it encompasses a lot of things, but it really is, you know, the basis of it, you know, is, you know, the documentation of the event. And so we can have a good indication and good knowledge of what occurred and how extensive the event covered. And also it helps us from the from our warning and verification perspective, because whether you know or not, you know, the National Weather Service, we are rated or kind of graded on, you know, our warnings that we issue for locations, whether it be a flash flood warning, a tornado warning, or severe thunderstorm warning. So we try not to overwarn. So we want to make sure that when we do put out warnings, that they're you know, for a good reason, and so that we don't tend to overwarn people and have people not pay attention to us. And the other part of the survey process is that it really allows us to work closely with people, especially in the emergency management community, to help share information and also, you know, allow us to get in and out of locations that can often be blocked off due to widespread damage, which is very similar to what happened in this event. So the process, you know, like I said, what, where, when, all that is very important. But we need as much information as we can get from emergency managers about where the worst damage is located. It's also very important for us to take that information and we can use that for planning, so we know where to send out our storm damage survey teams to see what type of damage occurred. And with this event back on the 13th of last year in April, we do this for other events as well, but we can provide the emergency management community maps, and you'll see one of those up in a moment, showing them the potential damage tracks, and we use that based off the MRMS rotational velocity tracks. So by giving them that information along with where we have reports of damage, they can give us the best information about where to go look when we begin to do that survey part in person. And there's just an example of one of those maps that we can, quickly create in the office, and then we can send those to our partners, and they can send people out to look in those parts of the counties to see if they had any damage in those locations. So like, Dan mentioned earlier, just in the previous presentation, the enhanced Fujita scale with ratings from, EF0 to EF5, and like Dan also mentioned, in the record, we have not had a EF5 in South Carolina. That doesn't necessarily mean that one didn't occur before records were kept, but as far as we know, there haven't been. But when we're looking at the damage, we're using damage indicators and the degree of the damage that occurs. So I wanted to show a little bit of an example of what we look at. We use this information. You can see the damage indicators on the left-hand side of the screen. And there's examples of things like small barns or outbuildings, manufactured homes, large buildings, different types of school buildings, and even things like light poles, flag poles, and obviously trees, and whether they're softwood trees like a lot of what we have around parts of South Carolina with pines, or if they're like hardwood trees, like some of our oaks and things like that. So on the right, I did just a small example of how we look at the degrees of damage within those, and I pulled up one example of looking at power lines or electrical transmission lines, as it says. And you can see the degree of damage there. It goes from 1 to 6, and we have like an expected range of wind speeds that would cause each type of degree of damage from 1 to 6. And we have a lower bound and an upper bound, and you can also see that graphed at the bottom of that. And for example, if we were to go out and do a survey and we saw, wood poles, power lines or whatever that were leaning due to wind that was either from a tornado or from strong straight line winds, we may come up with an average of, winds could have been around 100 or 110 miles an hour. So those are the kind of things that we use when we go out on the damage survey to try to determine how strong the winds were that produced the damage that we see. And obviously, you're going to need to do some things. You're going to have proper attire when you go out. You just can't go out in flip-flops and shorts. We need to have our damage assessment toolkit, which is where we actually put in all of our information, such as pictures and locations. Our little hotspot that we take with us when we get in places where we, to give us, connectivity to the web, and our little reference binder with the damage assessment, degrees of damage. It's built into the DAT, but it's also handy to have sometimes pictures. And obviously to put together some sort of map and storm tracks that we can use to know where we have to travel. And with the damage assessment toolkit, basically we get to a location. We can take a picture of that event. We can determine, sometimes it takes more than one image, obviously, and multiple locations along a track, but we can input whether it was from a tornado or a wind event. We can also put what the damage indicator was, the degree of damage, and then obviously a wind speed and any kind of comments or injuries, or if there were any fatalities with that area. And then that all goes back into a web viewer type of device, part of the DAT. And we have to go in there and we actually have to QC the data, and we also have to draw the maps showing the damage path and the track of the storm. So a lot of things help us with these surveys, especially nowadays with things when we can catch up with an emergency manager or a Forest Service official that has access to a drone. We don't have drones here at the office in Columbia, but Charleston is one of the prototype sites testing that. So we would like to think that maybe someday in the future we would have the ability to do that. So we use the maps that we provide and that we put together, and we do a lot of crisscrossing to check out those paths. So some other things to throw out. This is something that we were able to use in the 13th event, was this European Sentinel-2 polar orbiting satellite, which was able to show basically vegetation scars. This helped us, especially with the tornado that went across, the two tornadoes actually that went across the Savannah River site. If you've ever had access to that site, much of the site is just covered in is wooded, and there's not a lot of access to all of the locations. But this actually gave us the ability to know that there was a tornado in that area, and that you can see it via the satellite. And just another zoom. It's hard to see, but this is where Dan was talking about, where the two tornadoes crossed each other, right there just west of the town of Neces and Livingston. And you can see on the left-hand panel, you can see, it's hard to see, but there's two dark lines there. You can see where they crossed. And on the right-hand side, you can see where we plotted those damage paths, and you can see where they crossed there in that one section. Just want to show this. It's a little video here of helicopter footage, and this is of the Preserver Road location. Unfortunately, this is where we have the two fatalities, and you'll see the damage to the couple, to the mobile homes. The initial mobile home you'll see will be where the two fatalities occurred, and the other you'll see where we had some injuries. And it's amazing that when you see the actual footage that anybody was able to survive the tornado. Yeah, so wanted to get into some other things. The video was very instrumental in looking at everything. But when we go out and do this surveys, initially we don't have access to those types of things like helicopters, at least initially at times. But for some interesting stats, that day, if you add up all the tornado paths, we had over 122 miles of tornadoes that we had to investigate. Of course, our longest path for our tornado was the one that went through Aiken and Orangeburg counties, which is over 38 miles. So you're thinking, wow, we have all these. We have a lot of ground to cover. So you got to remember, most of this area is rural. Obviously, when we get out there, things that make this can be very challenging is people in South Carolina, Georgia, this part of the country are they're very much go-getters, and so they want to try to clean things up. So between people and the county and DOT, they begin clearing things up often before we even get there. So that makes the job of looking at the damage even a bit more difficult. Building codes can vary from state to state and even within a state. So when you're looking at damage, you have to keep that in mind as well. And then you realize that this whole process is taking much longer than we expected because we have to meet with our partners, we have to meet with the media. You try to speak with those that are affected because you want to listen to their stories. And logistics such as conducting these interviews with the media and meeting up with the EMs, and if you can get a chance to do aerial flight or partner briefing. So all these things contribute to the fact that it's going to take, obviously for this event, it's going to take more than one day, and it's going to take more than one team, because typically teams, when we send them out, it's usually 2 people to a vehicle, and we send them out to all of our locations that need to be investigated. So we take lots of pictures and do lots of interviews, and these can be very long days, and they often run from the early morning hours into the evening hours. And we try to make the information as accurate as possible by QCing all those data points and making sure that the times that we have entered in for the points and the radar all make sense. So, and then we have to put together public information statements about what occurred with each event, and we also try to put that information out in a visual way that can be easily done on social media. So some things that made even this event even more difficult was the fact that we had the pandemic. It just began. We were just in the early stages of it, and so it made it more challenging because we weren't allowed to have 2 people in a vehicle. So each survey team had 2 vehicles. We had 1 person in each vehicle, and so we sent out as many teams as possible, and it took a while to get to all of the locations. It makes it difficult when you're a one-person show in a vehicle because it can often be very distracting. You're trying to juggle answering phone calls from, could be the emergency manager, it could be the person you're working with. It could be just looking for damage, obviously just trying to drive. We implemented having walkie-talkies to talk with our partners that were in the vehicles either in front of us or behind us. And we also had to make sure that when we came in contact with people, that we were socially distant. And so we had to be careful in that realm where we were talking to media, people that were affected by the tornadoes, and with our emergency manager partners. So like I said,
left,
okay, I'm almost done. And just like I said, there's some, like I said, typically, without a pandemic, we would have 2 people per team. It's much easier to drive, have 1 person as a driver and 1 as a navigator. The ability to have, with good, proper staffing at the office, we can have 3 teams out, that's 6 people, 2 people per vehicle. That makes the survey process much more efficient. And then, of course, some things that can happen that may impact it is not having all the information about the areas that are impacted. So we end up spending more time in areas than we anticipated because we end up finding that the damage was much more widespread. It's also going to be things to be cognizant of is when you're looking at damage and you want to go into someone's property, make sure you ask that that's okay. And it's very beneficial to have the emergency managers from those counties with you when you're going to talk to people and try to get access to their property to look at the damage. And there's always the possibility, some people, it doesn't seem to be as much of an issue in this part of the country, but in other parts of the country can be very suspicious of people driving around with government tags. So that's just one more thing to think about. And like I said, a couple more things. When you're out there doing the survey, you always want to make sure that you're visible. So when we're walking along roadways and looking at damage and things like that, we've got colored vests on, very visible to anybody trying to drive by. Like I said, always ask permission to go on someone's property. Just don't assume you can do it because you're part of the weather service and you're there to see the damage. And then, of course, always watch your step. because when you go to, whether it's been a microburst or a straight line wind event or a tornado, there can be a lot of damage. And especially in rural areas, you got to watch where you step, especially this time of year when snakes and critters are out and about. And also when you're in the area where there's a lot of, say if it was a home that was damaged or things like that, have to look for trees and power lines that are down, as well as have to look for nails sticking up from boards. So it's always good to make sure you have safe shoes to wear, and just be careful of where you're walking and cognizant of those things. So that's all I have from doing storm surveys. We also find that we see lots of interesting objects out in rural parts of South Carolina. So just wanted to thank you for listening and attending this PAM session here for our lunch hour. So that's all I have, Frank.
All right, thanks. Very good, Leonard.